Hello everybody, and welcome back to the channel. Today we'll be doing a quad combo video of 4 different services, which we're all going to build in one video because they're all pretty damn similar. So hopefully we can get through it within an hour because I have to get a haircut after this, and even besides that, I've done myself the absolute favor of eating a ton of chicken wings and protein shakes today, and at some point I may need a 15 to 20 minute break to go spill out my guts. Anyways, let's go ahead and jump into this thing because I need to get started. Alright, so let's go ahead and dive on into it. So today we are going to be doing Instagram, Twitter, Facebook, and Reddit. Well, that's obviously a lot, so let's actually talk about the features that we plan on supporting. I assume all of you use at least one of these things, so you'll probably understand what I'm talking about when I say we're going to try and support a newsfeed. And in addition to that, we're also going to be supporting Reddit-style nested comments, where the comments themselves basically form a tree. You can have some top comments, and then you can also have load more buttons that are going to quickly fetch basically the next branch of comments below that. So hopefully that makes sense. Let's go ahead and move on to some requirements. So we've got a few different objectives in a problem like this. Oh boy, my throat is already starting to get sore, but I'm going to push through it. So the first is that, of course, we always want to be able to quickly load who we're following and who follows us. Those are just 2 common features of all of these applications. Additionally, we want to be able to get all the posts for a given user. I say this because when you see our eventual solution, this isn't necessarily something that comes for free with that. We need to be able to support this as well. Eventually as well, we want to be able to support a low latency newsfeed. Making a newsfeed is easy. Making it quick is hard. There are a lot of talks from Twitter engineers to prove this. Number 4 is that we want to be able to support configurable privacy types. This isn't that hard, but someone did ask for this in the comments of the last version of this video, so I figured screw it, why not throw this one in there. And then they also asked for Reddit-style comments where they can be infinitely nested. Now, if you're thinking about the use patterns of something like a social media site, hopefully it makes sense that 90% of the time that you're on there, you're probably just lurking and reading stuff, and you're posting pretty infrequently. So as a result, the main thing we want to keep in mind here is that we're going to be aiming to optimize reads as opposed to writes. That is going to be very important. Okay, so let's start thinking about some capacity estimates. Let me zoom in a little bit here. So the first thing is that I'm going to assume there are 100 characters a post. Get that one from Twitter. Even though it's 140, let's do 100 for making the math a little bit easier. Around 100 bytes, because a character is basically a byte. And then additionally, let's estimate that other metadata like user ID, post timestamp, stuff like that adds another 100 bytes. So maybe we can assume that there's 200 bytes in a single post. Additionally, if we have 1 billion posts per day, which is actually pretty realistic for some of these sites, you could be looking at 73 terabytes per year of storage. That's a lot. It's actually not a ton when you're a platform like this and you make a ton of money through ads. 73 terabytes a year is pretty little, but we are going to need more storage than that. We'll discuss that later. Additionally, let's assume that the average user has around 100 followers. I personally have no followers. I like to just tweet into the abyss. And that there are some verified users with millions. For example, myself, all the women in the world follow me. Next, we also have comments. I'm going to limit those to 100 characters for simplicity's sake. And again, that means they're probably around 200 bytes in total to store that. And also, when we start to think about comments and making them infinitely nested, it's important to have a sense of, how much data comments for a post actually take. I'm going to assume there can be up to 1 million comments per post, and that means up to 200 megabytes of storage required, because 1 million times 200 bytes. Okay, so the first thing that we're going to talk about is starting to fetch our follower/following. So the issue here is that we want both of these operations to be very fast, right? We have this one over here where we get the followers for a specific user, and then we also want to get all of the users that a specific user is following. And we want both of those to return quickly. Now the issue with this is that if you were to choose a database table that is indexed in a manner such that it is either by the user ID for all of their followers or the user ID for all of their followings, that is going to be very slow for the other type. The reason why is that these queries are going to be distributed. So if we look over here on the right side of the screen, let's imagine that we used this type of table over here, right, where we've got one user and then a follower ID, and that represents a following relationship. And then we go ahead and index on that user ID. So you can see the user ID field is sorted. That's why 4s are at the bottom, 6 is at the top. And then let's say we go ahead and partition also on that user ID, because there are going to be a ton of follower-following relationships. We're not going to be able to store them all on one database table. And so that's going to be really good when we want to find all the followers of one particular user. However, it's going to break down in a distributed setting when we want to find all of the users that a user follows. So let's say we wanted to find all the users that user 1 follows. So that would be this guy over here. As you can see, because we are partitioning on basically the person that has a following, getting all of a person's users that they follow is going to be very challenging because we would have to do a distributed query. We wouldn't have any indexing within those nodes. We would have to do a linear time sort, or rather a linear time scan, to go through every single row on here and every single row on here, and then we would have to aggregate them somewhere on some other server, and then we would have to return that back to the user, and that probably just isn't feasible. So what I've opted to ultimately do instead is use an actual derived data change data capture type of method. The reason I opt for something like change data capture here with one source of truth table is the fact that it helps us avoid partial failure scenarios, because keep in mind that if you're a client and you're writing to 2 different databases at once, this is one database, here's the other database, one of these writes could fail, one of them could succeed, and really the only way to guarantee that doesn't happen is going to be something like 2-phase commit, and that's going to be really slow. So if we really want to ensure consistency, another thing that we could do is use something like change data capture, and then use one of our coveted stream processing frameworks to ensure that none of those writes get lost. You can actually use one of the tables, as shown over here, and you would use CDC from it to basically go into something like Kafka. The reason Kafka is good is because it's replicated, so it's fault tolerant, and it is also basically a persistent log. So we know that if a message doesn't get processed in the moment, we can always go back and process it later. And then we've got something like Flink, which if you recall is going to checkpoint state occasionally. And this is going to make sure that we're never not processing a single message. And then we can basically take it and update our other table. And this is going to be our derived data. So you may notice that I've chosen to have the user followers table be the source of truth. That means for user X who follows X. And if you recall, that schema looks something like we've got our user over here, and then all the people that follow them on the right, and we index by that user ID, and we can partition on that as well. So then, of course, we've got Flink listening to all of those different partitions and then uploading another table, keeping it in check. Now, you may think to yourself, well, it is possible that Flink, in a failure scenario, might upload duplicate messages to the user following table. That's really not a huge deal because at the end of the day, a duplicate upload can just be deduped, right? Like if I have 4 and 22 and then I have 4 and 22 again, I could just say, well, if it's already in there, just don't add it. Not a huge deal. Okay, so now that we have kind of an idea of how we're actually going to maintain our follower relationships within databases, what type of actual database should we be using to do so? So of course, we do want to have good read speeds and good write speeds for these tables, especially for this guy over here, because it doesn't have any buffering before the writes get there. It's basically just taking all the writes as they come in. So it's important that we also do have some fast ingestion here. So in my opinion, I think something like Cassandra would be really good. Cassandra is very good in terms of its write throughput for a couple of reasons, one of which is that it uses leaderless replication, so writes can go to any replica. Another is that it uses LSM trees, so writes are first buffered in memory. But the point here is that, like I mentioned, we don't really have conflicts or write conflicts to worry about in the relationship of kind of a user and their follower, because at the end of the day, you're just merging them all together, right? Like if I say that a user has one follower on one replica, and then I say that a user has a follower B on another replica, the kind of combined state of those two is just great. Now this user has 2 followers. So again, write conflicts, not an issue. And this was unlike our tiny URL video where they were certainly an issue. So again, this is good for the reasons I mentioned over here. It's going to be fast. And basically, what should our partition and sort key be if we are going to have a database like this, especially for our user follower table, because that's where we really care about the latency. So my thinking here is, well, the obvious thing to partition on would be the user ID, right? Because we're already indexing on there. We want all of a user's followers to be on a single database node or a single database partition, because that is going to make the queries a lot faster. We don't have to do any, aggregations after we hit multiple partitions. And in addition to that, by actually sorting on the follower following ID, this just means that if we ever need to delete a row, say a follower stops following a person, we can go hit that partition, quickly find their follower, and then go delete that row. So, the example would be, here's partition 1, here's partition 2. You may notice that obviously we're not using just range-based sorting, or else number 6 would be on this partition and number 18 would be on the other partition. We're using a hash range sorting, or rather a hash range partitioning, because ideally that is going to load balance our tables a little bit better, keep the partitions more balanced. Consistent hashing, yada, yada, yada. You guys get it by now. If you don't, I recommend watching the tinyURL video and the consistent hashing video for some more details there. So we've spoken about how we actually want to go ahead and make our follower and following tables, how we're using derived data and change data capture to keep those up. And it's very important that we actually have those in check, because they are crucial for actually maintaining a newsfeed. The reason why is that for any given user, we need to know who follows them. If I post, it's very important that basically all of my followers are going to see my post, and so we need to be able to do that. And then, of course, once we actually go and take a person and basically all of who they follow, then you have to generate all the posts for them. So kind of the naive way of doing this is, you've got a client, right? This is the reader of Newsfeed. The first thing they could do is potentially hit the user following table. Now, to clarify, that's just who X follows. So that's going to respond with some people, and then they're going to go and reach out to the post DB, which is probably going to be sharded on user ID, because that is the most rational way of doing things. And then it's going to aggregate them all on one server, blah, 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 and return it back to the user. And the reason I said this was naive is because all of those distributed queries and then the aggregation step is probably just going to be too slow. You're basically bottlenecked by whatever the slowest query could possibly be, and that is a bad thing. And hence, this is why I call this the naive way of building the newsfeed. In reality, what we would like to do is put in a little bit more work on the write path so that we can speed up our read path a little bit more. So let's actually start to talk about that. Here's what I would call the more optimal newsfeed. So the first thing is that we should recognize that if we really want to make a newsfeed as fast as possible, we would somehow have to index all of the tweets by which newsfeed they belong to. And the issue with that is that you can't obviously do that, because it belongs to many different newsfeeds. In fact, we even said it belongs to around 100 of them, because the average user has around 100 followers. So the issue is that, because there are so many different places to put this tweet, we would have to end up storing a ton of data. Well, how much data actually? We estimated there were around 1 billion tweets a day, and there were around 200 bytes a tweet. And what if we did actually store 100 copies of every single tweet and put it in a different index? Well, we could, and then we would actually only have 20 terabytes of tweets per day, which, if you think about it, is really not that bad for a company like Twitter. I mean, they have literally millions of dollars of servers. 20 terabytes is nothing for them. And especially if we want to make this really fast and throw it in memory, let's say we had 256 gigabyte super beefy hosts where they actually have that much RAM in them. That's only around 80. Maybe we can round that up to 100 in-memory caches. And so effectively what we can actually do is go ahead and cache every single user's newsfeed. And we can do it on one of these super beefy servers. Maybe we've got a couple of replicas of them, so maybe instead of 80, it's more like 200. But that's okay. Again, these are massive sites. They make lots of money. 200 massive servers is not going to make or break things for them. So let's actually start looking at the newsfeed diagram, or at least the initial sketch of it. Again, this is going to be a lot to ingest, so no worries if it takes you a little bit to put this all down. You can always pause the video and go back for a second. So let's say that we've got client 6 over here. The first thing they're going to do is make a post. That's going to hit our post database. Note that again, I'm using change data capture here because it keeps everything consistent and we don't have to worry about two-phase commit. That is then going to be ingested into a Kafka queue for the same reasons that I mentioned before. This gives us fault tolerance and it gives us replayability, which is very important for this guy here, Flink. So in this case, as opposed to just ingesting one stream of data, this Flink consumer is going to be getting data from two sources. The first is going to be the user followers table, which if you recall from before is going to be that source of truth, which means that whenever a following is done, it goes right into this table. And so what's going to now happen is that this user, or rather this Flink consumer, can cache who follows user 6. Pardon me as I accidentally erase when I mean to write. But the gist is that, as you can see, Flink is going to look at all of those user-follower relationships, and it can actually shard itself on that user ID of this table. So keep in mind this table is user ID, follower ID, and the good thing about that is that these guys can be sharded the same way, because keep in mind PostDB is also sharded by user ID. And so now Flink, or a particular Flink consumer, only has to hold a subset of this data, and so it can keep it all in memory. And so let's see, now Flink says, okay, well, we know that this post has to be delivered to user 1, user 10, user 22, and 44, and then it's going to go ahead and write to the appropriate feed caches. We can load balance and partition these feed caches such that they each have certain ranges of users that they represent. And then the Flink consumer can figure out where it needs to send it. It'll probably have to reach out to Zookeeper, hit a load balancer, and then boom, there you go. Now we're in some caches. So let's quickly look at a couple of our notes to clarify things. Basically, Flink can go ahead and keep the state of all the followers, as I mentioned. And the reason that this is so important, that it keeps this state, is because it is a major optimization on having to make a network call to the database every single time, saying, well, who does user 6 actually have as a following? That would be very slow, and in addition to that, it would be a ton of repeat computation. Additionally, as new followers come in, we're actually streaming that data up to Flink via change data capture, so it is up to date. We don't have to worry about that. And then again, we talked about sharding. We're basically sharding on the poster ID, which is the user ID here, and the user ID which the PostDB is also sharded on. So this Flink consumer should actually be able to handle all of this data because we can partition it in a smart way such that there's not enough to overload it. Okay, so we've spoken about that, and then additionally you may be thinking to yourself, well, this works great for new tweets, but what if we want to edit a tweet? What if we want to potentially update security permission changes on it? What if that tweet all of a sudden gets new followers? Well, keep in mind that all of this data is actually flowing through into this Flink consumer, and then it can do the necessary logic to send those updates to the required caches. Now, of course, keep in mind, this is pretty expensive, right? Objectively, it is now taking a tweet a very long time to get into one of these newsfeed caches. But at the same time, it doesn't really matter if a tweet takes a while to get there, because all that matters is the user sees their tweet hit the PostDB, and then they think they're good. And then maybe 5 minutes later, it gets into everyone's caches, but they don't have to know that. It's all asynchronous. And at the end of the day, this is going to make everyone else's reading experience a lot better, and they're going to keep coming back to our site. So let's actually go ahead and talk about our post database and schema, because I kind of brushed over that. We haven't really mentioned it very much yet. And it's important that we do keep this fast, because in the case of the user followers table, it's actually the same thing. If writes are going directly to this guy, it needs to be able to ingest them quickly, or else it will become a bottleneck in our system. So for the same reasoning as before, I again wanted to use Cassandra, but this time I wanted to partition it in a slightly different way, where I would partition by the user ID so that you keep all posts from the same user on a given node, and then within a given partition, we want to use the sort key as the timestamp, or rather the timestamp as the sort key, and this means that when we run a query, let's say we've got 69, and then what's today's date? We've got 11/20/2023. Now when I load all of these posts, they're already going to be in pre-sorted order, and that's going to keep our query very fast for when we say get posts of a specific user. And again, that's what I mentioned over here. It is going to make sure that basically partitioning for a given user is nice and fast, and as a result of that, that endpoint will be reasonable. Okay, so we've gone over our actual table schema for the PostDB, which ensures that if we do want to load posts for a given user, that should hopefully be decently fast. It should all be on the same partition. It should already be pre-sorted by timestamp, which is great. However, we do come across one big problem, which is going to be popular users. So I did mention that some users are verified, and they're actually going to have millions of followers. So the problem with this is that our previous step of basically uploading all of our posts using change data capture and then basically using a bunch of different newsfeed caches as our sink is going to fail. The reason being that when you have millions of followers, that post has to get delivered to many, many different places, and that is going to be heinously slow. So what could we potentially do instead? What we're going to try to do is use a hybrid approach. So in this case, let's imagine that we've got our newsfeed reader. So our bad post would exclusively go to the PostDB and aggregate. Our ideal approach is that we exclusively read from the feed cache. But it's possible that what we could do instead is say only for the verified users we want to read from the PostDB, And for the non-verified users, basically we can read from our feed cache and then we'll aggregate those. Ideally, it'll result in a lot fewer partitions of the database that we'll have to hit, but even still, we are still going to hit a bunch of the partitions of that database, and that could still be too slow. So how could we make this a little bit better? Well, what we could do is introduce a potential caching layer for our popular posts. So the nice thing about this is that when it comes to popular posts, or rather posts from popular users, we actually know in advance that they're going to be popular. If someone with 1 million followers is going to make a tweet, we know it's probably going to get at least 10,000, 100,000 views within the first few minutes. And as a result, when that person makes a post, we can actually preload a cache so that everyone else can load it. So what this is going to look like is actually going to be very, very similar to our previous setup to load all of our newsfeed caches. For example, here's me. As I mentioned, all women on Twitter follow me. They love me. So the first thing that we do is put it in our post DB. This is going to be common amongst all tweets. The next thing that it's going to do is go over CDC. I forgot to write out the Kafka queue here, but hopefully that makes sense, into Flink. And then similarly, what's going to happen is that we've got our users table over here, which contains for a given user ID whether that user is verified or not. And so again, over change data capture, this can go ahead and hit Flink, and we can again shard this by the user ID, right? So again, shard by user ID. And so this way, when a post from Jordan hits Flink, Jordan's verified status is also going to be in Flink. And so as a result, Flink can say, oh, Jordan is in fact verified. All the ladies love him. Let's go and put one of his posts in the popular post caches over here. And so by using this style, we accomplish a couple of things. The first is that, one, we don't have to use a traditional write-through based caching approach where we would have to either use two-phase commit to ensure cache consistency, or just in general, we would have to have a partial failure scenario where our cache might get uploaded, but our database wouldn't, or our database, the write goes through and the cache doesn't. So this makes sure that everything is consistent, keeps everything asynchronous, and it also allows us to see whether or not a given user is verified when they actually make a tweet. And again, the nice thing about this is that post edits will also go back through here, back into Flink, and then we can go ahead and upload our popular post cache. Assuming that we shard these caches by user ID, we know exactly where a given popular user's post is going to live, and that makes our life super easy. So what do things actually look like again? Well, now the gist is that if we want to use our hybrid solution, we would basically also read from the cache. Okay, let's figure out where I'm at, because now even I'm starting to lose track. So, kind of the next thing that I want to be touching upon here is the following concept. We have mentioned that we want to read all of our popular posts from a popular post cache. However, a challenging part of this is that for a given reader, right, let's say this is the reader, it's going to the Newsfeed service, feed service, and then it's going to, popular posts, popular, and newsfeed cache, newsfeed. The only way that we actually know what to read from the popular posts is by figuring out who this guy follows that is verified. And that in and of itself could be a little bit of a tough query, because even though we store all of our follower-following relationships already, and that's decently fast, in order to actually get a sense of whether or not a particular person that I follow is verified, I would have to join that on the users table, and that could, of course, become slow. So how can we go ahead and do this? Well, again, we can use derived data. You might start to figure out a pattern here, which is that I do love me some stream processing, and I love using derived data, because derived data allows us to pre-compute data in the most optimal format so that we can make things as fast as possible. Now, how could we actually do this? Well, yet again, we could use another Flink node. We could have our users table, which already exists, sharded by user's ID. We could have our user following table, which, if you recall, is already a piece of derived data. So we're actually now using change data capture on derived data. And then what we do is by merging these two things into two different streams that go into the same Flink node and partitioning properly, we can actually tell for a given user not only who they follow, but if they're verified. So from the user following table, I can say, for example, I know user 10 follows user 3 and user 22. From this table over here, I can say, well, I know user 3 is verified. And you might say to yourself, shoot, well, it seems that the users table actually has to put verified users on every single Flink consumer. Every consumer. My argument to you here would be that there aren't that many verified users. I can't imagine there would be more than like 10,000 of them. And so a 10,000 person set is really not a big deal. But the gist is that as a result of having this small verified table in memory on every single node, we can quickly tell, oh, you know what? Hey, user 10 is actually now following user 3. That person is verified. Let's go ahead and upload to the cache over here. And now we can see that user 10 is following verified user 3. And we can use this as a cache to figure out my verified following. So for example, if I'm following Mr. Beast, if I'm following Donald Trump, if I'm following Obama, it would all be in this verified cache. Cool. So let's quickly touch upon security levels in posts, because this was a specific request for this video and I would like to honor that. So let's say that a user can actually specify whether a post is for all of their followers or let's say a close friend followers. So we'll keep it simple and say that there's only 2 configurable levels right now. However, it is going to be the case that this kind of scales out to 3 or 4 or 5 levels of potential security anyways. So the easiest way to implement this, at least in my opinion, is just by actually going ahead and putting all of this information in the followers table. So we already have our user followers table, which defines the relationship that these guys are having with one another. And so for example, we've got user 1, follower 2, so that means that 2 follows user 1. And you can see that their security level is all. Same goes for here. User 3 follows user 1. Their relationship is close friend. So recall that in Flink, oh boy, nice voice crack there. In Flink, we actually have access to this data. So it would say something like 1 has 2, which is an all follower. 2 all, and then 3 close friend. So when a post comes in, post of close friend, it can say, you know what, I'm actually only going for this guy here and not for all. And so as a result of that, we can actually continue to use our existing posting pipeline by just storing this data as well within our Flink consumer. Now it is unfortunate that basically changes to the specific close friend level of a follower or following will take a while to propagate through our pipeline. Same goes for a post, but they do all eventually go through to this Flink consumer who can then upload the caches or update the caches accordingly. And so that is going to make life a little bit easier. It's expensive, it's asynchronous, so if there's a post out there that you already made and you're like, oh shoot, that wasn't meant for everyone, this is meant for close friends, you changing that level is not going to make that happen instantly. And that is a trade-off here, but it is worth noting. Okay, so this is the part of the video that I definitely want to focus on a little bit because I think it makes this video unique. I haven't really seen too many others on the internet that focus on nested comments all too much. So let's talk about them. Basically, we want to be able to optimize to read nested comments. And the question is, well, how can we actually go ahead and partition those? Let's start with kind of the easy part of this setup. Well, keep in mind that when we did our capacity estimates for this video, we said that probably per thread, there's around 200 megabytes of comment data. And the good thing about that is 200 megabytes is actually very little. And what that means is that we can actually keep all of the comments, even on our most popular threads, on a single node, which is huge because then it means we don't have to do cross-partition queries. All that we have to do is shard by our post ID, and we should be good there as far as partitioning goes. The next question is, what about replication? So replication is a little bit more interesting because of the fact that we can actually have causal dependencies on comments and things wouldn't make sense in certain scenarios. So let's say we have a multi-leader database, as you can see right here. Here's leader 1, here's leader 2. So let's say that one guy is going to make a comment on leader 1 over on the left, and then a second guy, guy number 2, is going to read it and then respond to it on leader 2. And now the issue is that the state that leader 2 is in doesn't make sense because it has a comment that is a child of a comment that doesn't exist. And so that would obviously be problematic. When they sync up, maybe things will be okay, but anyone who reads from this replica in the meantime is going to take a look at that and be like, I have no idea what's happening. This doesn't make sense. So for this reason, I think that I would opt for single leader replication here. Could you maybe get away with quorum consistency in a multi-leader setup? Maybe, but at the end of the day, some of the replicas still might not make sense, and that would be a problem. Okay, so let's actually think about our nested comments a little bit more abstractly. So as we can think about it, if we have nested comments, that's going to be a tree, right? This could be comment 1, this could be the kid of comment 1, this could be the kid of comment 1, here's another kid of that one. And so we have all of this tree right here. And of course, depending on what site you're on, these comments are going to load in a different order. Some of them do it where basically you'll load a comment at a time, and it'll show you the next comments that you could potentially each click on. Some of them, like Reddit specifically, will actually kind of load a branch at a time, where it'll be like, oh, well, actually, let's load these two right here when you click the load more. And that's more of like a depth first search, right? The other way that I just showed was a bit more of a breadth first search, or at least it would show you everything at a particular level so that you could click into it. Now, I personally think the breadth first search approach is pretty easy to implement because you basically are just saying, well, you know, this guy can point here, this guy can point right here, and then every time we land here, we just do a query in our database for all of them that have, you know, a given parent ID. So you do like where parent ID equals X, and then you just index on that parent ID, and that makes it nice and fast. I personally, you know, I want to make this video a little bit hard and make everyone think a little bit, so I'm going to choose to try and think about this more from this perspective right here, where we're trying to actually get like a depth first search, single branch of comments at a time, because that's a little bit harder to do in a fast way. So let's actually go ahead and think about this. One approach that we could possibly take is a graph database. So how would this work? Well, if you haven't heard too much about graph databases in the past, I have spoken about them on this channel, but I will give a quick recap. So there are basically two different types of graph databases, one of which is going to be called a native graph database, and the other is a non-native graph database. So let's talk about non-native first, which I've illustrated over here on the left. So a non-native graph database, especially in the scenario of comments, would look something like this, where every single node has an ID, it's got a parent ID, and then basically you've got all of the things that they contain as their data. So the issue with this is that I've already kind of mentioned that if you want to do a depth first search, you would say, okay, well, I've got my ID over here. Sorry about that. I can't really draw on the left side of the screen. And then you would say, well, find me all of the nodes with parent ID 1. So sorry, I indexed this guy incorrectly. But the point is, you would say, find me all of IDs with parent ID 1, blah, 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 over here. And then you would get these two, and then you could continue to depth first search as you please. The problem with that is this. When you have an index on a particular field, the time complexity of finding an element based on that field's value is going to be O of log of n, right? Because we're actually going to be binary searching this table. And the problem with binary searching a table is that that gets slower as the table gets bigger. So even as this table gets bigger, even if the branch of comments that you're looking for is the same size, it's still going to get slower. And that in particular is why non-native graph databases are bad. On the other hand, native ones are quite a bit faster because they actually just go ahead and use pointers on disk. So obviously I've drawn out a tree right here, but the gist is you can actually just put a pointer to another memory location on disk, and then they're literally jumping around. So to do a depth first search, I would actually just follow these pointers all the way down, and then we're good to go. Nonetheless, native graph databases are actually not that fast. The reason being that jumping around on disk is slow. The first thing I covered on my Systems Design 2.0 series is that a disk looks like this, right? You've got a little wheel, you've got something that points around the wheel, and to jump from place to place to place to place means that you actually have to find that location. And because these are mechanical parts, this is not like RAM, it's just really slow to do that. And so this is potentially good for, graph type data models, but if we can avoid representing our thing as a graph type of data model, we could potentially do this better. So what we're going to try and actually do here is build a depth first search index. And yeah, I'm just not going to talk about breadth first search that much because I don't think it's that hard to do. So let's go ahead and see how we could try and do something like that. So before I actually get too into this one, I'd like to go ahead and thank Systems Design Fight Club for inspiring me a little bit here. I've taken a solution and adapted it a little bit, but the general idea of this thing is that the depth first search index that we're going to build is very similar to a geohash. So if you think about it, when we look at a particular comment, let's say every single comment of a given node has a letter A based on if it's the first child, B on if it's the second child. If we had a third one, we could call it C and put another node here. And every time that you have a child of a particular node, you again restart that kind of sequence. So what you do is in our actual index, the ID of the comment is going to be the full path of it. So this guy right here is AA, because it is the child of A and it itself has the letter A, and so that's why it's AA. So what does this actually buy us? Well, let's say that we wanted to get the entire contents of this branch right here. Well, what is this branch? Really, it's everything that is to the left of letter A and before AB. So the range query would look something like A to AB. And if you look in our actual comment index right here, you can see that A, AA, AAA are all right before AB. So then we can just stop right there. And as a result of that, we can perform a nice clean range query. So even though the time complexity is going to be O of log n, and then however many entries we have to pull after that, this potentially is going to be quite a bit faster because it is enabling good disk locality as opposed to jumping around every single place on disk. And so all we have to do is just generate this comment index by appending all of the comments names in the chain. And so when we click load more, it should actually be super easy to go ahead and make that range query and hit our database. So keep in mind that I wanted this to be a single leader replication, and something like MySQL I think would work just fine for a database like this. Okay, so as you can see, guys, we've now gotten to the point where we have an absolute behemoth of a diagram to go through. So I'm going to attempt to do it nice and slowly. Let's say right here we've got our poster. This is the guy who is literally going to write a tweet or a comment, and there are going to be many different things that happen when they do. The first thing, I'll start off at the top, is going to be our user service. I drew one box, but ideally all of these services should be horizontally scaled out. You can have a load balancer in between them. I just literally didn't have enough space to write it out. So keep in mind that we've got our user service, we've got a user database, and I elected to use MySQL there, the reason being that I don't think that many changes are being made to profiles, so I'm not too worried about write throughput. I'm more so worried about actual consistency of user changes, and having a transactional single leader database like MySQL I think is perfectly good for this. Single leader replication I think is very reasonable here. The next thing that I'll cover is our follower service. So the follower service, as we mentioned before, is going to be in Cassandra, or at least the follower DB is. I wanted the user follower DB, where basically for a given user who follows them, to be our source of truth, the reason being that we could then stream those changes right into our Flink node for eventual delivering of posts. I also noted that we should be sharding on our user ID here. If you recall, our schema is literally going to be user ID, follower ID, security permission. Hopefully that makes some sense. The next part is the post service. Like I mentioned, this guy needs to be able to ingest writes very quickly. Posts happen all the time. I thought Cassandra was the right choice for this one as a result of that. Again, this is something that you can be sharding on user ID. The last part of this is the comment database, which, as we touched just a moment ago, I wanted to be using single leader replication. The reason being that we have causal dependencies in comments, and as a result, I want writes to be as up to date as possible. So using something like MySQL I think will be pretty reasonable. Totally understand if you think that the write ingestion is not going to be fast enough there. If you can think of a single leader database that uses LSM trees, maybe that would be better. Could be something like HBase. Who knows? So now the thing is that we've got all of these change data captures, and this is where we start reaching the middle of our setup because we have all of our Flink nodes. So we've got two Flink nodes. The first is what I would call like the following Flink node, because this is going to help us generate all of our derived data in order to actually make faster queries for things like loading a user's following or figuring out who they follow that is verified. So if you recall, we've got one user service telling us who's verified, and also who we follow. And we can output that into the user verified following cache. This is going to make that query as quickly as possible when we actually have to go ahead and load up our newsfeed. Additionally, we also want a user following DB because I want to be able to quickly see, hey, how many people am I actually following and who is that? And so we are going to go ahead and do that over here. I wanted to do that in Cassandra because, again, I think that for single partition reads, Cassandra is actually quite quick, especially if you have a good database schema where you make sure to partition everything by the actual user ID. So that would look something like user ID and then following ID. So this is the person they're following. Cool. So we have our user verified following cache. Put that guy in Redis. It's not going to be that much data. I think keeping it in memory is pretty fair. You can replicate this as much as you want. You can shard it out, probably based on user ID. I think that's all pretty reasonable. So the other type of Flink node that we have over here is going to be our posts Flink node. So this is going to take in new posts over here from change data capture. It's going to take in effectively users to see who's verified, so that verified posts in particular can actually go to the popular post cache. And then it is also finally going to take in the follower table changes so that we can say, hey, user 6 has user 1, 2, and 3 following them, so deliver those to the corresponding caches. It could also then say user 10 is verified, so deliver that post to the popular post cache. Now the last piece of the puzzle is obviously going to be the reader. This is going to be someone reading their newsfeed. So as we mentioned, reading your newsfeed is pretty simple. The first thing that you're going to do is go ahead and hit the feed service, number 1. Then you're also going to reach out to the user verified following cache because we need to know which verified users we want to load posts for. That way we can hit the proper shards of the popular post cache over here. Once we do that, we can get all of those results that we need back. Same thing goes from our particular newsfeed cache. It's just going to be from one of these replicas, one of these partitions, and then they can actually get aggregated over here on the feed service. You can aggregate them by timestamp. It's not going to be more than like 100 posts, so it shouldn't be too hard to do that. And then you go ahead and return it right to the user. Similarly, there are a few other queries that the user is going to read, one of which is going to be, hey, who am I following? That comes from over here. There's also, hey, who follows me? That comes from over here. There's also, hey, what are my user stats? What does my profile look like? That comes from over here up top in the user database. There's also, hey, what are the comments that I'm trying to fetch for this post? That comes from the comments DB. And then, of course, finally, there's, hey, what have I posted before? Or what have other users posted before? That would come from our post DB. Anyways, guys, I know this was a very, very long, in-depth, massive video. And frankly, I may have even gone through it faster than I needed to. I don't mean to brush through any parts, and I absolutely want to keep this one as clear as humanly possible, but my main intention was to try and leave no stone unturned. There are definitely a lot of practical considerations when it comes to a design like this, and I think it's very easy to make a video that skips over some of the in-depth details of a lot of them. I could certainly see a lot of people not loving this design just due to the amount that I abuse change data capture, but I also do think it's a very good way to ensure that all of your data is actually in sync without having to use two-phase commit or introducing yourself to a bunch of partial failure scenarios. As always, though, my solutions aren't perfect. I'm making these up myself. I'm not just going to other channels and copying them. So please do go ahead and critique me in the comment section, ask questions, ask anything you want, and I'm happy to defend myself. Of course, you can always get me, and you're probably going to be right. Anyways, guys, I hope you enjoyed this video. I will see you in the next one.